Okay, we're 10 o'clock on the dot, so I'll get started, and then I'm sure some more people will join us as we get on with the morning. So, good morning, good afternoon, or good evening to everyone who's joined us here today. Thank you for coming to this webinar. Today we'll be discussing the SOL-REC2 project, which targets the development and implementation of strategies for better separation, sorting, and recycling of multi-layer material waste consisting of layers of polymers and aluminium. Our speakers today have all been working very hard on the project and will be able to give you a much better insight than what I can into everything behind the scenes. But just before I hand over to the team, for those who haven't heard of us before, we just wanted to give you a quick introduction to the TWI Innovation Network, or some of you may already know us as TWIN. And to do that will be Dr. Jem Selchuk, who is the Head of Business Development for TWIN. So thank you, Jem, and feel free to share your slides.
Thank you, Chloe. Good morning, good day, everyone. I'll talk a little bit about Innovation Network before you dive into the miracles of recycling and multi-layer materials. So let me share my screen, and I hope you can see this. Is that looking all right?
Yeah. Yeah.
Okay.
Pop it in a big.
Let's go with a bigger screen.
There we go. Perfect.
Okay, thank you. So what you see in the picture is TWI in Cambridge headquarters, and some of you may have been here before, but it's been a historic site. Almost everything in Cambridge developed around TWI in many ways in terms of industrial activities. So I'd like to a little bit talk about TWIN, the setting, the presence in UK, Europe, and global. Activities cover multiple dimensions: industrial, academic, lots of partnerships with universities. We have UK centers, which is convenient for people to work in different regions, and also strong presence across Europe, working with unis and SMEs, and I've had so many collaborations over the years. A little bit of info on the UK presence. Hopefully you can see the map and where we are. Headquarters in Cambridge, presence in Wales, further up north Rotherham, and then east, northeast Middlesbrough, and further up north near the North Sea operations Aberdeen office, typically used for training activities. Innovation centers, this is something that we've been working on for almost over a decade now, and with our first center back in 2010 with Brunel University, we have opened up several centers with different partnerships, and you can see that the map is very populated. And we've also jumped across Europe with international partnerships with Sabancı University in that time. Each center, each university has a specific theme, so it's quite easy for typically companies to align themselves with, depending on their interests, and hopefully, everyone has a nice match, and sometimes they get the opportunity to work with different centers at the same time. Our most recent addition is Arden University, and we hope to expand activities in that direction further. It's to do with the industrial photonics. Global presence. TWI has been active across the globe for many years, and almost can have you can see a track record in pretty much every country, almost continent, quite intensively, and therefore it's good to know this for global activities. Track record in terms of collaborations of what we have achieved. As I said, we've sort of captured it for over a decade. So this 2009 to 19 is a good bracket in that respect. And if you look at the numbers, the scale of R&D funding that's been created is huge. A quick breakdown shows that almost half of it went to universities and research organizations, and more than half went to industry, helping them to achieve better efficiencies and innovation capacity. 365 projects and activities, over 1,000 companies, and many over 150 RTOs and universities have been our partners over the years. Twin components, this is a quick diagram to make a note of. As I said, there are different sections here. The TAP, the Technology Acceleration Program, is typically there to help SMEs, small medium enterprises, to increase their capacity in collaboration with university centers where they need research support. And also we have the Structural Integrity Research Center that we set up nationally first. We're now looking to internationalize that, and that's educational, you can say postgraduate industrial PhDs and master's studies. The top left is private partnerships. That is typically for large enterprises who want to align their strategic plan, roadmap with TWR projects so they can get good support. Some further numbers and to show that it's quite a diverse and inclusive community, over 150 companies, and that number has increased, in fact, quite significantly, and 20 countries across the network. So, people join for different reasons, the network, some mainly for networking, some for events like this, and the others for idea generation and profile purposes. So there's always a reason to be part of the network. We have a specific team that works closely with the network members, and it's the Technology Innovation Management team. Basically what they do is they go hand in hand with the companies in terms of idea generation and concept development, and helping them to put strong applications with twin members, and therefore they have a good success chance when applying for funding for product process development. Because we are quite, we have a physical presence in Cambridge and across the country and also globe. There are also, this is a good diagram basically for startups and new companies if they want to be part of the setting and already benefit from the setup that we have. It's also possible through office presence and further tapping into the talent pool, etc. Very good for SMEs and startups, I would say. There are various reasons, as I mentioned, why people align with the network. This could be technology readiness level, bringing innovation to markets, secure grants, link up with resources. The university centers have strong resources. Some companies may not have R&D resources, and therefore that's a chance for them to basically work with the innovation centers. And therefore they're up to date with latest applications. There are mechanisms to join the network. I wouldn't go into that this moment in time, but if anyone is interested, there are subscription packages, and I'm sure there'll be a package that meets people's interest in and motivation in joining the network. Consultancy support, obviously, on innovation management is big for us, and we're heavily involved in that respect in terms of project ideas and opportunities, and bringing the network's members from industry to academia to come together and work together and collaborate. We do several events like this and meetings during the year, some physical, some online. We had a great convention in July, which was physical at Cambridge, and over 200 people come together after a long time. So, there are very good opportunities to come together and meet and discuss. So in that respect, the affiliation with Twin often helps meet innovation challenges. Project management support, if anyone needs, is also something they can receive from Twin. The projects like SOL-REC are European projects, often, long duration, big budgets, multiple partners. Could be difficult, could be easy for some, but I think the wealth of experience is available, and therefore, if there's any help needed, it's possible to receive that from the network. Events, as I said, meetings, bringing people together is very important for us, especially at times when people couldn't meet in person. Info days, calls for funding. We're trying to align people as much as possible. giving them opportunities to pitch their ideas and partnering, and therefore have events regularly like conventions, summits, and we are a phone call away. You can see my details at the end of the slides. A couple of examples for those who might want to relate to. I mean, this one is a UK one. It's a quite an advanced project in terms of laser processing, and its whole purpose is to basically help manufacture battery packs in a better way. Our member company is there working with our innovation center, Brunel, and TWI supporting. So do have a look at that. Training activities also available. Our member companies get that, and in this particular case, European project management, very strong subject, important for proposal success, grant management, and therefore being a member of the network, you'll get support on these and help with your applications and gain more success really at the end of it. Some useful links, do have a look, as I said, network website, centers, acceleration programs for SMEs, and also media and events section is quite active, and you'll get a lot of information. Hopefully we'll have this is an online platform that we're building, and it will be a one-touch shop online where you can go and pick services and support that you need, and therefore it's a good mechanism to be part of the community and streamlining many things at the same time. So hopefully you can be part of this too. We'd like to thank sponsors. We had many over the years. They are strongly supporting twin activities, and companies, SMEs, alliances, universities that we had always get the opportunity to sponsor events and gain basically exposure in the activity in doing so. So everyone is welcome to engage in that. We thank them gratefully. These are my details. I hope to hear from you, and thanks for the opportunity. Thank you, Chloe.
Excellent. Thank you very much, Jem.
We'll just stop sharing. That's okay?
Yes, sure. Yeah, thank you.
Thank you.
Perfect. So thank you, Jem, for that introduction on the TWI Innovation Network. If anyone has any questions about the network or for Jem specifically, please pop them in the Q&A box and we'll get back to you. Alternatively, as you saw Jem's email, please send him an email and be able to answer any questions. So now, without any further ado, I'll hand over to George to introduce himself and the project and the team. If anyone does have any questions throughout any of the presentations today, again, please pop them in the Q&A box and we'll go through as many as possible at the end of the session. So thank you, George.
Thanks a lot, Chloe. I highly recommend everyone to contact Jem and the team and boost your productivity and innovation efforts through your collaboration with Twin. A lot of opportunities there, and definitely a wide range of projects. We're covering the full array of technologies and industries in that respect. So hi from me, I'm George Sidisopoulos. I'm a senior project leader at TWI's Polymer and Composite Technology Group, and I specifically sit in the Novel Polymer Technology section. Within the NPT, as we call it, we serve a wide range of industries, basically every industry, but the main industries that we serve and collaborate and have had the opportunity to interact and obtain know-how and to a high level technical expertise into the peculiarities or requirements or impact, let's say, of aging through our failure investigations has come through our interaction with these industries, which are part of either TWI's membership network or innovation network or innovation partnerships. So throughout this interaction, we have gained quite a high level of knowledge on the complexity of polymer materials, specifically for our section, and the various compositions that one would face and the effect of their exposure under certain environments and conditions. And this, of course, feeds into the prior knowledge and know-how, and of course, a very good understanding of the barriers, technical and non-technical, that one would face when it comes to end-of-life management and, of course, recycling. So within the NPT, we focus on 4 main technology themes: polymer joining and whatever's involved in that respect, joining of non-similar materials, specific joining requirements to withstand, let's say, certain conditions, coatings and materials, the development of specific material coatings that will provide the desired properties, and development again of characterization techniques that will allow you to pinpoint and define either the state of the material or its composition, bespoke training to a range of areas, and of course, plastics recycling and sustainability. So for us, a polymer, if we were to describe it in the simplest form, is just it's a combination of monomer units that are bound covalently in a unique chain, as you can see here. That's the simplest way that one could describe a polymer, which comprises a plastic product. However, in reality, it looks something like this. Your polymer will have various entanglements. It will have a hydrodynamic volume in which you will have certain voids and areas where, depending on the application, one would like to have those voids remain, or in case they want to remove those voids or reduce them to increase barrier properties, especially for semi-crystalline polymers, one would have to introduce either nucleating agents or other chemical agents to obtain the desired properties. In the same respect, to in some occasions, to have certain, let's say, properties like transparency, those voids are necessary. And of course, in every case and occasion, when you want, for example, UV resistance or environmental resistance, you have to introduce agents. For marketing purposes, we introduce colorants. So it's not just the polymer itself, you can understand. And when it comes to manufacturing, those additives and changes go into play. And of course, it's never just a simple polymer chain, as you can see here. It's not just one polymer unit. It's not, you might have the same monomer unit. So for example, let's talk about polyethylene. Its building block is ethylene. It's never polyethylene itself. It's a bit more complicated. So let's assume it looks something like this. You may have side chains. You may have different geometries, different architectures that will have an impact in its overall mechanical properties. So these are important when addressing or facing the issue of recycling, because through certain routes and methods of recycling, you can obtain, let's say, separation of certain materials based on density or other physical properties. However, it's very difficult to separate, segregate, or obtain a homogeneous product within the same group or family when you have, for example, let's say, differences in architecture, which will, of course, impact in differences in properties such as MFI. MFI to the average consumer and maybe to the audience might not be important, but if for the processors that will reuse these recycled products, it is very important. Not to mention that in some cases we have functional groups just for specific applications. The chemical manufacturers and resin manufacturers know about these agents or functional groups, but in most cases these are confidential and need to be somehow identified or registered. And not to mention, of course, at the end, as we described earlier, we always add additional additives to provide the desired properties. In most occasions, for environmental purposes and where aesthetics are not important, we add fillers such as carbon black. But in almost every application where you have weathering, you will have environmental agents, some cases flame retardants, and that will limit its application after the item has been recycled. And again, the overall objective is to have a product that, although it is complex, will provide the desired properties. And this, of course, does not come by a simple chain alone. So, for example, if you want to tailor things like spherulite size, as you see here, this is a bit top level, but this will have an impact on the mechanical properties. You need to introduce agents that will affect the chain properties, entanglement properties, and other properties which we know. So I believe through this short description, you can understand that we have a good understanding, not just about the technical barriers or the material limitations themselves, but also through our interaction with the various companies. We understand the economic barriers that come with either the production of these materials itself and also the recycling, regulatory, and of course, environmental. What is the impact of reintroducing certain material types into the market? What is the impact and cost associated, and so on and so forth? So we therefore developed the plastics recycling and sustainability theme. These are our main theme members. I'm the lead member of the theme, but we also have with us today one of our presenters, Anna and Talava, Alan, Chris, and Amir, who are part of the team, and of course the greater group and section within TWI. So within this theme, we provide advice on material selection that will, of course, provide this possibility of circularity by design, simply because of the complexity of the materials themselves. We can provide advice and consultation on certain additives to enhance the material property, determine its service life. The service life determination in some cases is important because it will correspond to the aging effects on the material, and therefore its properties over time. So for example, you have some cases you might have chain scission, which of course will impact the overall properties down the line. Product design, so this lies more into the region of composite or the end product that you will see to increase its shelf life and longevity, and of course on material properties and the proper end-of-life management strategies that one should apply in order to increase their returns and reuse of their capital investments in either materials or products or specific types. So when we assess or consider a recycling condition, we always like to look at the energy and cost requirements, because when it comes to an industrial scale or a global scale sustainability, we'll look into these things. It's not just the carbon footprint. If it's not cost effective, somehow in the larger calculations of the life cycle analysis, one will find that cost is paramount in this area, and the environmental impact of either technique is linked to this. So the obvious way to avoid going through the recycling route and the many devastating impacts of improper waste management is banning single-use plastics and plastics overall. However, we must bear in mind that plastics have introduced and have made our life more sustainable. They have reduced loss of either food or other products. They have maintained and reduced, for example, weight of certain materials and products, and therefore fuel requirements or energy requirements for their transportation installation. And they're far more versatile than other materials, simply because we can tailor them, albeit it's becomes a very complex product. So you can see here that mechanical recycling is the less intensive approach. However, it comes to with a certain price. You can only, it will reach a plateau or barrier of the quality obtained of the material. So other applications are necessary. And recently, this has become a topic of discussion, especially with the EC. At least 2 deputy directors have highlighted that it will no longer be considered as recycling when a technique is applied and the recyclate is either energy, so that is not considered recycling anymore, or any type of oil that one could translate that can be converted into plastic. From plastic, it has to go into plastic to be considered as recycled. So as you can see here, depolymerization techniques that are commonly referred to as chemical recycling is probably going to need to change name when it comes to recycling, because recovery of the feedstock material is not plastic recycling, it is feedstock recycling. So there is a need for a clear definition of the term and technique. So as I mentioned earlier, depending on which technique you apply, you will get a specific type, and there are certain limitations. So overall, mechanical recycling, although is a very widespread method, it's highly efficient, it recycles large quantities and seems to address the issue of plastic waste accumulation. There are many limitations, and this again has been highlighted by the legislators. So the legislators now are talking about not just volumes of product reclaimed, but also quality. So quality goes into play, and we have to ensure that quality material comes out of the whole process. So in this respect, combinational techniques are required, such as chemical recycling or physical chemical recycling. There are wide definitions and I don't want to go into the terminology because it will only complicate things, and I guess the audience as well. So a combination of techniques is necessary to increase the quality of the material obtained, and not just in recycling techniques. Inventory management is key here. If you know what goes in, you know what comes out. If you are able to segregate to a high level, you will definitely reduce your operational costs, and we can describe what we're doing in this area as well through this project. So as I mentioned earlier, quality is a key issue. So normally with mechanical recycling, if there are no controls, no barriers, no inventory management in place, you will get a downcycled product, as we say. So downcycling basically will give you a product that is of lesser quality, not well defined in most cases. Of course, this depends on the supply routes, and for sure is limited in its applications. In most cases, it's used for lower end applications where you do not need specific material guarantees or to establish material properties. In the case of a closed loop system, your material that has been recycled can be used for the same purpose. So if we recycle packaging material used in a specific application in, let's say, the food and beverage industry, it can be used for the same application. This is, again, slightly more difficult and requires certain intricate technologies. There are some technologies out there, and of course, making them sustainable and cost effective is another question, but there is movement. And finally, upcycling is, I guess, the best option, and it's where the EC and many legislators highlight that we need to focus on. We need to focus on high quality materials that can be used in other market applications, simply because market demand and needs change over time. So you might have a certain recyclate, but the recyclate might change over time. The need for, let's say, a specific product might change. So removing certain chemicals or impacts of aging, such as chemical contamination or colorants or certain additives, is key here. So there are movements, and especially TWI has, through a different project, of course, ISOPREP has been able to work in this field as well. So for all intents and purposes for this project, we're looking at a closed loop system overall. So as I mentioned, there is a recycling strategy in place by many countries, and especially in the EU and US, they have set very ambitious targets, but we need to consider all these factors when we design a strategy to recycle a specific product line or from a specific source. We need to look into combinational techniques, and we need to acknowledge there are some complicated materials such as multi-layer packaging, as you can see here, or blister packaging, that are very complex. And it's a science on their own. So you have a combination of various different layers, and not just various different layers. Each layer provides a specific characteristic and property, and it is necessary to provide the requirement for transportation or storage of that product. Now, in the various surveys that we've done, most of the consumers, and of course my partner Zoe, would say it looks plastic to me. You can just toss it in the in your recycling bin and it will be recycled. This is wrong. So in this case, multi-layer materials, with the exception of a few products from very specific industries, can be actually recycled. The complexity of the materials plays a key role in this area, and separating the layers and delaminating or eclectically dissolving certain layers is key to obtain or to achieve the recycling of these products. It's very, very complicated. You have a very intricate science here, because in many occasions you have a wide range of layers. It's not just 1, 2, or 3 layers. It can be 7 layers, and we're talking about layers of different polymers with different properties. That is amazing how they were able to bind together. So it's top level technology here, and unfortunately there's a lot of pressure by society to ban any product that cannot be recycled, and in which case has moved suppliers and manufacturers to go towards monomaterial solutions, which we will explain down the line. But I would like to highlight that monomaterial product, although can be easier to recycle or can be considered more sustainable, in most cases comes with a cost. And for example, that cost might be the requirement of thicker layers, so larger polymer quantities, more oil being used, more refining processes, more higher carbon output, and a higher cost associated with the manufacturing and transportation. So we must consider that as well. So a possible approach to recycling these products comes through our project, SOL-REC2. SOL-REC2 is a project that is utilizing an inventory management system through the employment of digital watermarks through our partner Filigrade, and the application of a solvent toolbox system that we're developing that are not only green but also cost effective. So those two parameters have gone into play, so that this is a sustainable technique that will allow us to delaminate primarily, because delamination is more cost effective, more environmentally friendly, and if necessary, dissolve eclectically certain polymer layers from multi-layer systems. So through our surveys, we have determined the layer composition. But first, let me introduce the project and the team. As I mentioned, this is an EU-funded project. We have a budget of 4.6 million euros, and this project is being managed through the collaboration of 8 partners from 6 different countries, a very strong group of companies and universities and innovation centers. And throughout this project, we're focusing, as I mentioned, on the development of toolbox systems, so solvent systems, and not just solvent systems. We're looking at the whole recycling process itself that involves its primary separation, also called as inventory management, but also monitoring after the processing has taken place. So what happens to the material once it's removed? How is it identified in subsequent applications and manufacturing steps? So overall, our intention is to improve sorting and separation, and of course, to achieve and obtain the recycling and separation of the various layers, making multi-layer materials packaging and blister packaging sustainable and circular. So as I mentioned earlier, multi-layer materials are quite complex. So for this purpose, we've done various surveys to establish the concept of the population when it comes to recycling and the recycling of these products. Do they understand the difficulties that are associated, and whether these products are considered recyclable or not, and how they could improve this, and whether they're willing to contribute. So we have a clear understanding of that. And we also did a market survey and contacted various industries in this field to establish where this industry is moving, and focus our attention towards those materials and prepare a strategy towards the future and the future products that will be introduced. So overall, we've selected a certain variety of materials and compositions that represent the majority of the materials out there, and represent, of course, the various composition variations that you will face in a multi-layer product. We're looking at, of course, the separation, the establishment of an identification method and segregation and successful segregation of the products before they're recycled, and after their recycling, the possibility to identify the recyclate itself. Might sound complex, but we need to monitor each layer, because as I mentioned earlier, once we move towards monomaterial layers, certain additives and certain layers have not been erased. They are still existent, but they have been reduced to much, much thinner layers, and therefore are considered as, let's say, an additive of the material and not the material itself. It allows the reprocessors and manufacturers of the recycled, using recycled products to reuse and process, but that extra layer will still remain in the material itself. So a study of its accumulation over time, and various models need to be drafted so that we can monitor this material and ensure that we can reuse it for a set amount of times and period before, of course, we have to move to other techniques. And with that, I will set the floor for my colleague, Anna Antilava, who will talk and give you an idea about the composition of these layers, the multi-material layers, and possible solutions and technical difficulties associated. So let me just stop sharing.
Okay. Hello, everyone. I'm Anna Antalava, and in my presentation, I will talk about current trends in multilayer packaging and challenges with its recycling. So first of all, let's start with reviewing the plastic demand by industry. In year 2020, the overall demand by all the industries taken together was 49.1 million tons in European countries. And this increased demand is not surprising because plastics are a very versatile product. They are lightweight and they can be manufactured in a variety of colors, shapes, sizes, but at the same time, they're very cost effective to produce. And due to this, plastics found application in packaging. And as you can see from here, the packaging industry is dominating the demand of plastics, and it's the 40% of overall plastic demand by the industry. So let's look at the demand for rigid and also flexible packaging. And those types of packaging are used for consumer applications, but also for industrial applications. So if you look here, the rigid packaging for consumer application is dominating in its demand, and it's 44%. Then you have flexible packaging for consumer applications at 32%, and then the remaining goes to the industrial applications for the flexible packaging and rigid packaging. If we look at the polymer demand by polymer type in Europe, you can see that the highest demand is for polyethylenes. Those are for low density polyethylenes, as well as medium density and high density polyethylenes. Also polypropylene, polystyrene, and PVC and PET. And those polymers account for about 90% of all overall demand. And they are also increasingly used in packaging. For example, half of all the polyethylene production goes to the production of films. And those films are increasingly used in packaging, for example, for single carrier bags or as layers in multi-layer packs. And another type of packaging, which is blister packs, have increased demand for PVC. And I will talk about it in a bit. So what are multi-layer packs? They consist of several layers of different materials, and they got introduced by the industry because they're very lightweight. And at the same time, they provide a variety of functionalities depending on what types of materials you're utilizing. And also they utilize a lower amount of virgin material, but at the same time give the same functionality. And usually you have the composition of multi-layer packaging that ranges from 5 layers to 9 layers that are co-extruded or blow molded together. And a basic configuration of multi-layer pack consists of the coating on the outermost layer of the packaging, and this coating protects printing or labeling on the packaging. Underneath it, you have the outer layer that acts as a printing surface. Beneath it, you might have the structural layer. Structural layer gives packaging its shape and also protects it against tearing. In multi-layers, you might also have tie layers. Tie layers combine or adhere dissimilar materials, so they help these materials to stick together. There are also various barrier layers available, for example, barrier for oxygen, or there might be barrier for moisture or light. All depends on what's your application for the packaging and what are your contents. And in the innermost layer, the layer which is closest to the packaging contents, you have the seal. And seals are usually polymers with low melting points that can be heat sealed. And one of the requirements for sealants are that they must not interact with the packaging contents. So those are the basic layers that you might find in the multi-layer, and the composition of those, and also they might differ from different packaging. All depends on what's your application. Now let's review what types of materials are usually used and what types of properties they provide. So for the mechanical stability, you might utilize HDPE or polypropylene. Also, paper or cardboard is increasingly used. This gives packaging its shape and also protects it from tearing or any mechanical damage. For the oxygen barrier, you might have EVOH or aluminum layer. For the moisture barrier, it's polyethylenes are increasingly used. And for the light barrier, so UV barrier, you might have aluminum layer again. For tie layers, polyurethanes, and for sealant, there might be varieties of different polymers that can be heat sealed. So you can see that you can choose what type of materials you would like to use in your multi-layer packaging, and also choose what kind of properties you would like to have. So this is the packaging option, which is very customizable. And because of this, it's very popular in the industry. Another type of packaging is blister packs. In Europe, 85% of all solid drugs are packed in blister packaging. And there are two basic blister packaging types. One variety has a cavity made of clear thermoformed plastic, and the lid might be the combination of clear plastic or a combination of plastic, paper, or foil. The second type of packaging has the foil or aluminium as essential component for both webs and cavity, and it is created by cold stretching. So the main components of the blister packs are forming films and leading materials. And for the forming films account for about 80 to 85% of the packaging weight, and leading materials account for about 15 to 20% of packaging weight. And the most common types of blister packs, about 75% of them consist of PVC as the forming films and aluminium as the leading material. So as you can see, both blister packs and laminated pouches are very popular packaging option. However, if they're not treated and their waste is not managed properly after you discard them, it creates a problem of plastic pollution or accumulation in the landfill, because plastic or aluminium, which is increasingly used in the packs, those materials do not biodegrade. And it's actually estimated that about 50 billions of blister packs go to waste every year. And to look at the European recycling rates, so for plastic packaging, 46% of recycling rate was reached in 2020. But there is an ambition to increase this figure to 50% by year 2025, and to increase it further to 55% by 2030. So you can see that there is increased motivation to increase recycling. However, at present, laminate pouches and pharma blister packs are still not widely recycled. So the reasons for that are the challenges with their recycling. So for multi-layer packs and blister packs, one of the main challenges is the separation of layers. So the separation of various polymer types that you have, coatings, as well as aluminium layers. And another problem is collection and sorting. How do you sort these materials when there might be various compositions that you might not be aware about. So SOL-REC project is trying to address those two problems, separation, so delamination of layers, as well as sorting and advanced labeling of layers. And if you're not separating the layers, there might be difference in melting points and processing temperatures of various polymers, which creates problems such as immiscibility of polymer blends if you're recycling everything together, and there might be differences in the properties of polymer blends. Another very widespread challenge with the recycling is material degradation. And usually there are two types of degradations that take place. So there's the degradation during the recycling process itself. So there might be some thermomechanical degradation that decreases the quality of the final product. And another degradation is material degradation during the product's lifetime. So during the lifetime, product might be exposed to various environments such as heat, oxygen, light or moisture, and all of this affect material quality. And of course, after recycling, that this might have effect on your quality of your final product. There are also some challenges with the regulations. For example, what types of materials you can use in the food contacting materials or packaging. Within SOL-REC2 project, we conducted an industrial survey. This industrial survey was the consultation with key players in food and pharmaceutical industries. Those included producers of packaging, as well as end users of packaging. And we tried to establish and understand their requirements for multi-layer packaging, and also to understand what are the barriers for recycling of their packaging. So are they recycling their packaging now, or what's stopping them from it? And another point of discussion was, where is the packaging industry moving? What are the current trends? So during these discussions, we identified some of the clear trends that were highlighted to us. One of them is the move away from multi-layers due to challenges with the separation of layers, sorting and collection, as I highlighted, and to move to monomaterial. So industry is considering to use polymers such as polyethylene or polypropylenes increasingly for monomaterial applications. However, it presents challenges. So monomaterials will be bulkier. They will utilize more virgin materials. They also have worse mechanical and barrier properties. And the reason for this is that there's no single material that can satisfy all your desired packaging requirements and functionalities that you can obtain with the composite laminate packaging. Another issue that might arise is that when you have the monomaterial, you might have some printing on top, labeling, and you might also utilize coating that will protect it. So in a sense, that also presents a challenge of separation of different materials. Another trend that we saw was the move to paper-based multi-layers. So specifically, the target is to move to 95% fibers and 5% plastic. So from the consultations, we found out that currently paper-based cardboard packaging consists of about 75% paperboard, which gives packaging its structural layer, 21% polymers, and 4% aluminum. So the industry is trying to reduce use of polymers, tries to remove aluminum and increase paper-based layer. And those type of packaging are recyclable as they produce long fibers, plastic films, but also remaining residue, which is called polyol. However, this also raises question if this is recycling or the downcycling of products in terms of polymers and also the residue of polyol, does it lead to the closed loop recycling? And this is something that we need to work on, and with SOL-REC2, we're trying to obtain high quality final product, recycled product, the polymers and also aluminium layers. And the third trend that we saw was move away from aluminium layers, which is the removal of aluminium layer completely, or another option that was highlighted was to substitute aluminium layer with metallized coating, which is thinner, which again raises the question of and the challenge of separation of layers and separation of the materials in your recycling stream. And within SOL-REC2, we're trying to work on these challenges and propose the solution. And I hope that you found this presentation informative and that you enjoyed. Thank you.
Okay, thank you, Anna. Now we will have the honor for our academic professor, Andy Abbott, making a presentation on the techniques involved in solvent recovery systems. Professor Abbott has a very long experience with solvent recovery solutions, ionic liquids, and dipeptectic liquids, and will provide further insights in this area. Andy, over to you.
Thanks, George. Thanks very much for inviting me to talk today. So what I'm going to do is to talk a little bit about what we've got so far in SOL-REC2. Most of the work that I'm going to present today is a joint work between the University of Leicester and SOL-Ionic. So as we've just heard, so we just heard that laminates are ubiquitous. I think all of us have used the same crisp packet in our presentations. And we have it there for, as we've heard, a sort of barrier usually, or it may also be an aesthetic property. So one of the questions is, how do we physically or chemically look at that interface and try to separate those materials? So we've seen that there is some recycling of materials, although not commercially relevant at present. A lot of it is downcycled or goes into fillers in other applications. There are two processes on the net which talk about separation, and those are both covered by patents. And it appears, although there's very little out there other than the sort of patent information, that they're either based on organic solvents, which will dissolve up the polymer components, leaving metallic components, and then the polymers are recovered by evaporating off the solvent. Or the other is to use an organic acid, which will attack the aluminium at the interface and then separate the materials that way. So that's what's been done so far, but there's very little data on that actually in the literature. What appears from the literature data is that both are relatively slow, and clearly if we're going to have a viable process, it needs to be relatively fast. There are limitations, obviously, with using organic solvents. Clearly the cost is one. The biggest limitation clearly is the flammability. Organic acids tend to be corrosive, but they're also very volatile. And most of these processes that currently are out there work at slightly elevated temperatures. In both processes, there's going to be a significant amount of loss of the solvent from the process. So we need to make sure that we don't lose solvent to make sure that we retain circularity. And also the organic solvents, if we're going to recover them, the polymers from it, then we need to evaporate off the solvents. And that's clearly going to have a large energy requirement. So there are drawbacks to all of the current technologies. And so what SOL-REC2 is trying to do is to use a non-volatile solvent, and that might sound like an oxymoron, but I'll show you in a minute that it's a very common way of using solvents. And we're going to try to make sure that the solvent is not used up during the delamination process. And what we also trying to achieve is something that works at the interface, and particularly at that sort of adhesive layer between the different polymers and metal layers. What we're trying to do here is not purposely dissolve anything, so not really have a solvent, but really to have something that works, softens the interfaces and gets us pure layers, which can be split later. So that's the sort of dream, the ideal way in which this process would work. So the first thing we need to do is to get ourselves a solvent that is non-volatile. And this is why I've been brought into this project. So about 20 years ago, we came up with a way of making a solvent that didn't evaporate. So you take two solids and you mix the two solids together and you make a liquid, and that's called a eutectic, means from the Greek, means easily melted. And through a series of patents, we patented over 1 million of these binary mixtures, and we routinely use ternary and quaternary mixtures of components to be able to make a liquid. And the beauty of this is that you can tailor it to be either very hydrophobic, very hydrophilic, acidic, basic. You can change the properties a lot. So sort of, if you think about the sort of organic solvents which are commonly used in industry, there are about 30 molecular solvents. They say we've patented over 1 million different ionic solvents. And this might sound very difficult as something to do. I've done this, if it was a sort of face-to-face meeting, I'd do this practically for you. Here's component 1, in goes component 2. So this isn't speeded up, there's no solvents in there, no magic. What we do is we take the two components and we mix the two together, and miraculously we make a liquid. And you might look at this and say, wow, that is magic, but actually give it about a month or two, certainly in the UK, and you'll all be doing this. So when we take solid ice and we add a salt to it, then miraculously it turns into a liquid. And what we're doing there is we're making a eutectic. Okay, so we've got lots of chemistry to be able to choose from, and to be able to design something that will go into our polymer layers and hopefully soften up those the interfaces and allow the processes to be separated. So as part of SOL-REC2, we've devised a series of different liquids which will function like this. And what appears to happen is that the deep eutectic solvent has to go through the polymer layers or work at the interface from the edges. And so what we found is that it doesn't work particularly well at room temperature. And exactly as the same processes that we've been found in the literature, it seems to be that we need to go close to the glass transition temperature of the polymer. So that's the temperature when it goes from being a rigid polymer to being a flexible polymer. So we need to open up the structure of the polymer to allow our solvent to get at those interfaces and somehow work at the adhesive layers. So that's what we're trying to do with our process. We found that typically about 70 degrees, 80 degrees is a sort of temperature that our processes need to work at. And so the concept here is that we take our blister packaging and we try to get the solvent to go at the interface. And what we find is that the time taken to delaminate these layers depends very much upon the type of polymer that we have in terms of its structure, its density particularly, and it depends on the thickness of the polymer as well. So we have found that almost all polymer multi-layers can be split in this way, and so we've got a very nice picture on the bottom right of your screen of I think it's a 5-layer multi-package system. Again, this is a blister package that was used for tablets. And you can see quite clearly that we've got 3 nice clean layers. And typically this takes between about 30 minutes and an hour to actually get to split. Now that's less than ideal, but it's probably better than anything else that's out there at the moment. And what we can see from the photograph is that we get 3 very nice clean layers, which could be very readily recycled as bulk polymers. So we've got a technology that appears to work. What we find is that actually Obviously, if we have a larger sample, then it's harder for the material to go through the different polymer layers. But if we make the sample smaller, so if we sort of chop it into smaller samples, then we can get delamination times down to about 5 minutes, which can take us to a continuous flow process, which is clearly the advantage that we all want to have. Because as you make it smaller, then rather than having to penetrate from the top and the bottom out down to the interface with the metal layers, then what the solvent can do is actually work from the side in and penetrate that way, making it much easier and much faster. So again, it depends still upon the types of polymers that we've got, but our best separation time goes down to around about 5 minutes. And just to show you how simple this is, here we've got a vial of DP-Tectic, and what we can see is because of the density difference between the polymer, which is around about 1, and that of aluminium, which is sort of 2.5, 3, then we can see that the polymer will float to the top and the aluminium will sink to the bottom of the vial. So what we have is in principle a very simple method by which we can split our multi-layer packaging into its individual components. So the next step is that clearly we need to optimize this liquid. Clearly the cost of the liquid is a very important parameter. We would like to be below €3 a kilo for the liquid. We think we're there, although obviously with current situations, chemical prices are changing all the time. But the great thing is that the solvent isn't actually used up. A tiny amount is physically or mechanically lost in the process. But the liquid needs to have negligible toxicity, and we have examples of those which do. It needs to be non-flammable, and again, we have examples which are, and it needs to have low viscosity, which we're optimizing at the moment. So we are, with our colleagues, scaling this process up at the moment, obtaining the process parameters, and we aim to make a pilot plant early next year. And we're going to optimize the liquid and characterize its properties and perform a full techno-economic analysis. So hopefully what we can see from this is that our aims have been partly achieved so far. And we are able to separate polymers using DP-Tectic solvents. I'd like to thank my colleagues who have done a lot of the work here listed at the bottom. And I'd also like to thank the EU for funding this project. Thanks very much.
Thank you, Andy.
Brilliant, lovely. Thank you all for your presentations, and they're really interesting. And I think everyone's now, it's a very eye-opening project. Everyone's learned a lot more about what goes where and how everything works. So thank you all for your really interesting presentations. Appreciate we've gone a little bit over time, so maybe I'll just take 1 or 2 questions out of the chat box.
Well, actually, Chloe, I think we can answer all. Well, there are 4 questions that I can see. I think we can answer all 4. It's not going to take that
more
long.
than happy to, if you're happy to stay on.
So
please.
yeah, we can answer live.
Great.
So,
thank you very much.
is both thermoplastic and thermoset polymers, are they recyclable? Yeah, well, good question. And that brings us back to the term what we consider as recyclable and recycling. The main difference of thermoplastics and thermosets is thermoplastics you can modify by applying temperature, heat. But with thermosets, you have a cross-link system. And in order to recover the polymer itself, you would either have to depolymerize or delink those certain chains or link points, or overall depolymerize the thermoset itself. So we're looking at, in that case, monomer recovery. So it's difficult, but again, it's very complicated because it depends on the polymer. It depends on the thermoset. It depends on the linking agent. Certain linking agents have a chemistry that allows it to be reversible. Others do not allow this possibility. And again, it depends on the generation of the polymers. There are some companies that are looking at reversible thermosets. But then again, thermoset have a specific properties that make them necessary, at least in certain applications where higher temperatures are present. So I hope that answers the question. If any of my colleagues want to contribute, maybe, no?
Sums up there, George.
Okay, so next question was, what are the main constraints linked to manufacturing strength and recyclable plastics used for composite materials? Well, to make an introduction on this one, it depends on the composite itself. So if we're looking at long fiber composites, we know that one box is ticked. So mechanical performance and properties are primarily bound by the reinforcement layer, the reinforcement itself. So the properties of the polymer matrix are secondary, one would say, not highly at looking at mechanical properties. Of course, bondage is important in this case. So we're looking at barrier and other properties, which brings us back to the quality level of the recycler. So if you want to ensure, let's say, welding or weldability of the layers or miscibility of the polymer itself, then quality and purity and homogeneity of the polymer itself plays a major role in that area. So again, it depends on the polymer strategy applied, quality of the product obtained. What we are proposing here is the recovery of high quality products and a good understanding of the composition itself. So we could apply this. So for a short carbon fiber or short fiber composite materials or other nanocomposite materials, it's a bit more complicated, and again depends on the quality and purity of the polymer layer. Anything else that anyone would like to add? No? Okay. We have a defined reduction of factor of mechanical properties of polymers subjected to recycling. How much is roughly the reduction of stiffness and the yield stress of a classical plastic, PA6, for example, obtained by recycling in many times? Thanks very much. Well, again, we have to look into this in each case. For as far as this project is concerned, we're looking at our initial assessments and trials to primary waste, so waste that has not been used or has not been infected by other chemical residues or has been exposed to the environment, UV or other, because we're trying to assess a proper toolbox for the polymer and plastic itself. Then other factors will go into play and we will evaluate. However, to comment from our other knowledge in other areas, it depends again on the exposure of the material itself. So for example, if you're looking at polyamides, depending on the exposure, you will see a hydrolysis essentially or other impacts to the material, which could reduce the mechanical properties of the material itself. And that's why certain indicators that will give you feedback on the quality or at least on the aging of the material are important in this case. Shelf life indicators that will help our inventory management need to be introduced in this area so that we can determine not just when the product was manufactured, how long has it been sitting, and certain markers that will give you feedback on the exposed conditions and so on. Any contributions from my colleagues on this one? No? Okay, we have a question that's not relevant necessarily to recycling, but what type of polymer material is used for hydrogen barrier pressure vessels? Well, you can use polyamides. That's what you would find in most fuel cells, but high pressure vessels, it's an own technology. It's an intricate technology on its own. So barrier properties is something that we look at specifically the barrier and polymer layer. For the barrier properties, it's not necessarily the crystallinity that goes into play with this part in this particular case, because simply the molecule of the hydrogen size is very, very small. The chemical affinity or solubility, one would say, of the molecule itself with the polymer matrix has a much greater role, and we see this, for example, with the comparing polyethylene and polyamide 12. So in that case, simply because you will have a hydrogen bondage between the polymer and the hydrogen molecule, we see better barrier properties, although in a contradiction, the crystallinity and which corresponds to the voids, the microvoids present in the polymer matrix is lower for polyamides. So you have a larger amount of voids compared to polyethylene. So I hope that answered the question, but as my colleague Anna will share, and through her other projects, specifically looking into hydrogen and improving hydrogen barriers, it's not as simple as that. You might require different layers. It depends on the properties, it depends on the conditions, how long you want to store, what type, is it a specific medium, is it pure hydrogen? So again, another subject not very relevant to this one. And I think that's it. That covers, okay, so we have one last presentation. Is DES recyclable? What is DES? Andy, you're on mute.
So DES is deeply technical solvents. Yes, totally recyclable. So we've done many projects where we've recycled them at least 10 times. In this case, we're not envisaging they're going to be used up in the process, but we've got 20 years experience of recycling these things on a large scale.
Okay, thank you, Andy, for that. We covered every question, Chloe, so not too much over time.
No, absolutely fine. Thank you very much for staying on, everyone, to answer those questions. That was really, really great. So yeah, as I said, thank you everyone for joining us today. Hope you've all learned something new. And if anyone does have any further questions they'd like to ask the team, you've seen everyone's emails today. Alternatively, you can send myself an email, chloe.sparks@twi.co.uk, and I'll pass it on to the relevant person. But again, thank you all for joining us today. Thank you to the team for your presentations. Wish you all well and have a great rest of your day and week.
Stay tuned for the next one.
Absolutely. Thanks, everyone. Bye.